Hello everyone, it's a great honor to be here to present our work. I'm Zhong Weibo from Beihang University. My topic is correlations between kinematic flow components decomposed by Liutex and local flow patterns. And I'm going to make my presentation from the following 5 aspects. And as for the brief background, the local flow kinematics and the local flow patterns are significant features indicated based on the property of local velocity gradient tensor. The velocity gradient tensor decomposition based on Liutex provides a mathematical definition for the kinematic components of local swelling flow, thereby constructing a unified framework for studying velocity gradient tensor in turbulence. And the local flow patterns, which are also implied by VGT, are used to classify the local streamline geometry or topologies, establishing correlations between local flow patterns and the kinematic flow components can help identifying different flow structures, and especially the vortex flow structures in complex flow problem, analyze the kinematic characteristics of turbulence, and also help investigate the turbulence mechanisms such as the non-equilibrium effects, and the local flow patterns are also facilitate the incorporation of turbulence physics into turbulence modeling. So before the analysis, here are brief introductions to the identification methods of local flow kinematics and the local flow patterns. The Liutex decomposition of velocity gradient tensor provides a mathematical definition of local flow kinematic components, and the Liutex performs in the swirling flow where the discriminant of velocity gradient tensor delta is positive, and there are complex eigenvalues. In the transformed frame, the Liutex method obtains the rigid body rotation, the pure sharing of swirling flow, and also the relative swirling flow strength of compressing stretching factors. The Liutex-based velocity gradient tensor decomposition provides an effective approach to distinguish the components of local flow kinematics, including the rigid body rotation, RR, and pure sharing part SS, and the compression stretching part CS. And as for the identification of local flow pattern, or the local flow streamline topology, the most conventional methods is the QR plane, which is constructed based on the second and third invariants of velocity gradient tensor. And this method is proposed based on the incompressible or weakly compressible flow condition. And based on the invariants Q and R, the sign of the discriminant delta, there are 4 flow patterns in the QR plane, 2 for swirling flow and 2 for the non-swirling flow. And in this study, we focus on the swirling flow part, which is closely related to the vortex flow. And in the positive R side, you can see the flow pattern is alternating or compressing along the rotation axis with amplified orbital compactness. While in the negative R side, the local swirling pattern is actually stretching and orbitally damping. However, the three-dimensional local streamline cannot be uniquely defined by any point in the conventional QR plane. So to address this issue, Das and Kinematic rewrote the canonical velocity gradient tensor, and they use its magnitude g to characterize the scale factor or the size of velocity gradient tensor, and defining the structure velocity gradient tensor, or we say the normalized velocity gradient tensor, as the shape parameters. Thus, a new non-dimensional QR plane or normalized QR plane is constructed, as you can see in this figure, with a bounded region. It is a kinematic region. And moreover, the analytical boundaries of the kinematic region in the normalized QR plane provide additional information regarding the local flow kinematics and shape characteristics. As marked in this figure, the left boundary in red represents local flow free of pure shearing and only consists rigid body rotation and stretching along the rotation axis. The left boundary also represents flow in which the vorticity vector is adjacent to the large strain rate eigenvector E1, and the right boundary in blue also implies a zero pure shearing tensor, but it represents rigid body rotation and axial alternation. Here, the local vector alignment occurs between the vorticity vector and the least strain rate eigenvector E3. And the topmost point in the QR plane indicates an velocity gradient tensor condition involving only rigid body rotation. And the kinematics of the flow element at the origin of the QR plane is entirely attributed to pure shearing. The contribution of pure shearing diminishes as the elements move away from the origin until it vanishes at the boundaries. And the lowest boundary represents only the compression stretching effect. Okay, for more complex flow pattern under compressible flow condition and focusing on the swelling flow region, the novel local trace criterion is proposed by our group to identify complex vortex system. The magnitude of local trace criterion is defined as the first invariant of the new tensor psi, and the vortex regions are extracted by positive LT. A projection plane named as LT plane is constructed in positive delta space. Its apsis axis psi indicates the axial spiraling compactness, and its ordinate axis eta represents the radial spiraling compactness. And in the LT plane, the projection of positive LT is an elliptical region at the center of the LT plane. And the incompressible flow that's characterized by P equals to 0, this line, is a line across the original point of LT plane. So in LT plane, 4 kinds of spiraling patterns can be indicated in the 4 quadrants. And further, the 0P line can further indicate the compressibility information. Thus, 6 flow patterns in total are distinguished in the ellipse, and they are listed in this table. This indication method is the LTER indication. It can be used to deal with compressible flow problems with complex vortex structures. Then, the correlations between the kinematic flow components decomposed by Liutex and the local flow patterns are analyzed based on typical flow cases. And in this part, we are going to start with a fundamental flow under incompressible condition using the normalized QR phase plane. The database employed here is the forced isotropic turbulence data from the public Johns Hopkins turbulence database. And the establishment of a connection between the kinematics and the pattern of the flow is achieved by conditioning the statistics of the structural properties of the velocity gradient tensor on the normalized invariant QR plane. And consequently, the influence of the scale factor of the velocity gradient tensor is excluded herein. The conditional average results of the scale factor G are presented here first. It can be observed that the higher mean magnitude of velocity gradient occurs when Q is positive, and it reaches the highest at the boundary top, where the streamline is nearly pure rigid body rotation, and a tail with relatively large velocity gradient tensor scale also exists along the right zero delta line. Then the conditional average distributions of different kinematic components in the normalized QR plane are analyzed respectively. First, the component directly related to the rotation is discussed here. And as indicated by the mathematical derivation of QR plane, the ridge body rotation reaches its maximum at the top of the boundary, and the contribution of ridge body rotation decreases from the top point as it approaches to the zero delta line. And from the perspective of flow patterns on both sides of the r-axis, the overall structural ridge body rotation intensity carried by the actual stretching pattern on the left side is relatively lower than the right side. However, the conditionally averaged distribution of lambda Ci, which represents the swelling flow strength, is almost asymmetric with respect to the r-axis. The analytical relationship between the ridge body rotation factor phi and the lambda Ci indicates that such difference between them arise from the distribution of the pure shearing component S1 along the rotation axis. So further, it can be inferred that the distribution of S1 is also not symmetric with respect to the r-axis or respect to the flow patterns. So we subsequently analyze the results of the pure shearing components. The pure shearing effect is divided into two parts for analysis, and the S1 is the component along the rotation axis, and the S23 is the other shearing component, which is perpendicular to the rotation axis or on the rotation plane. The results show that the shearing component along the rotation axis S1 is high when vortex is under stretching pattern, while the shearing component in the rotation plane is enhanced when vortex is actually compressing or actually alternating. However, the conditional average results of the total pure shearing strength indicates that its distribution is symmetric about the r-axis and is independent of the flow pattern. And the compression stretching effects conditioning to the incompressible flow patterns are shown here. The left figure presents the results of structural stretching rate as concluded from the mathematical derivation of QR theory. There is no compression stretching effect on the 0R line at the positive Q side, and the compression stretching effect becomes higher as it approaches to the lower boundary. The right figure shows the actual compression stretching effect normalized by the swelling strength, which corresponds to the aforementioned actual spiraling compactness. The spiraling compactness level decreases from the line of zero actual stretching rate and reaches the lowest spiraling compactness at the zero delta line. And spiraling compactness is almost independent to the distance from the original point. So this actually corresponds to the evolution of the 0p line on the LT plane from the origin to the edge of the ellipse. Then we extend the study on this correlation to the strongly compressible flow condition. At this point, the QR plane method is no longer applicable. Therefore, the LT plane is employed to investigate the connection between more abundant flow patterns and the flow kinematics. The flow database is a transient flow field of a supersonic compression corner flow controlled by a micro vortex generator obtained using LES. And the Mach number is about 2.3, and the total grid number is about 39 million. The LES result has been validated by comparing with the DNS result. And from the conditional average results of the ridge body rotation factor and the swelling flow strength, The highest rotation intensity occurs at the origin of altiplane, whereas the compression stretching effect is weak. In other words, strong rotation appears under conditions of high spiraling part compactness, and the distribution of rotation intensity near the two branches of the 0p line is relatively symmetric. And this characteristic is consistent with the basic laws previously obtained in incompressible flow conditions. The conditional averaged results of the pure shearing components demonstrate their close relations with flow patterns. Strong pure shearing effects are consistently observed on the negative p side in this site, which means the flow is in an expansion state. Furthermore, the average intensities of different pure shearing components exhibit significant asymmetry across distinct flow patterns. In this compressible flow case, the pure shearing components, particularly the S23, which is projected on the rotation plane, are notably stronger when the vortex flow is spiraling with axial alternating or axial compressing pattern. So these are all about this study, and here is a brief conclusion. In this study, the correlations between kinematic flow components and local flow patterns are investigated. The local flow kinematics, including ridge body rotation, pure shearing, and compressive stretching effects, are mathematically defined and decomposed by the Liutex method. The local flow patterns are identified based on the normalized QR plane for incompressible flow and based on the LT plane of local trace criterion for the compressible flow. The results under incompressible condition shows that the rotation effect is averagely strong under high spiraling compactness level, but they are almost independent of the local flow patterns. The pure shearing component along the rotation axis dominates in axial stretching pattern, while the shearing component on rotation plane dominates in axial alternating pattern. The spiraling compactness level related to the compression stretching effect shows an approximate orthogonality with the distance to the QR plane origin. And correlations are also analyzed in a compressible flow case where the flow patterns are more complex. The most important difference is that the pure shearing components are averagely stronger in the axial alternating pattern with expansion state. These research findings contribute to exploring the utilization of local flow characteristics based on the velocity gradient tensor to establish a stronger connection with more complex turbulence features. They provide support for the research on flow mechanisms and facilitate the development of turbulent flow models that are more accurate and easier to implement. Okay, that's all about our research, and thank you for your listening. Thank you very much.